In section 1.9, we're going to take what we learned in 1.8 a little bit further and actually look a little bit more carefully at linear transformations and how we can think about finding the matrices that actually represent them. So just as a quick reminder from 1.8, we had looked at the way that this box was transformed using the concept of a linear transformation. Right, and so we're thinking about that in this case as matrix multiplication, matrix A times X. And it turns out that this little 2x2 matrix, when you multiply vectors that are in this box by this 2x2 matrix, it distorts it into this box. And so we talked about how in this slide we're kind of acting on matrices in a linear transformation rather than thinking about just plain old linear combinations of the columns, right? And so this can end up distorting a picture, so to speak. And so we're going to do similar things in this section, but talk about, hey, how do we actually get that matrix? That's sort of the focus of the current section. And the way we approach it is by using this theorem. So theorem 10 here in section 1.9 starts with the notation we learned in the last section. Right? So this T colon Rn to Rm means let T be a linear transformation such that it takes vectors in Rn and sends them to Rm. Let's let that be a linear transformation. Then that means there must exist some unique matrix such that this is an important relationship here, such that when you apply the transformation to a vector x, it's the same thing as just multiplying that vector by a matrix. Another way to say this is that every linear transformation can be written as a matrix and can be carried out via matrix multiplication, right? That's literally what this is saying. If a linear applying a linear transformation T to vector x is the same thing as multiplying it by A for some matrix A. And moreover, the second part of the theorem tells us how to actually find that matrix. The m by n matrix A has jth column T of ij, where ej is the jth column of the identity matrix. In other words, this is the form of the matrix A. Right? So the jth column is the transformation applied to the vector E sub I. And so E sub I, it's talking about the identity matrix. So we're going to start this discussion by reminding ourselves the identity matrix and what E sub I is. All right, so we had learned this in a previous section. What we had learned was that the identity matrix is the matrix that has all zeros in it except along the diagonals. So it's all zeros except there are the number ones on the diagonal. And so depending on what dimension we're in, it has different dimensions, right? So for example, in 3 dimensions, I sub 3 would look like this. Right? All zeros except ones along the diagonal. Now, what this is saying is EI, your E sub j, whatever j is going to be an index, is the jth column of the identity matrix. And so in I3, E1 would be the first column, E2 would be the second column, and E3 is the third column. Okay. Now, again, this matrix gets bigger depending on what dimension we're in. Right? So I4 is going to be a 4x4. I2 is a 2x2. And depending on what dimension we're in, with the n dimensions, then there's going to be n E sub i's. Right? So when you see something that says E sub j, like let's just say E sub 1, right? The number there means that there's a 1 in the first spot and there's zeros everywhere else. But we don't know the dimension necessarily in this case, so my pen's running out of ink here. Give me one sec. don't really know what dimension we're in. So when we write down E sub 1, all that means there's a 1 in the first spot, everywhere else there's a 0. If we write down E sub 2, that means there's a 1 in the second spot. Right? E sub I, there's a 1 in the I spot. Etc. So in general, when we say the jth, this definition right here is telling us that the jth column of a linear transformation matrix is T E sub j. Apply the transformation to the jth column of the identity matrix. It's a very common question. It's a common test question. We're going to look at a bunch of examples in the next couple of pages. Right? Every time we want to figure out what the matrix is, we're going to apply the transformation to the jth column of the identity matrix. Because what we'll see in the next section or in the next chapter is that these columns form a basis for the space that we're working with. So by just applying the columns to the basis, i.e. these columns, we're able to figure out a general expression for that transformation. This next couple pages, the subsequent pages here, are just some examples of doing that. So we're going to do it first with that contraction mapping that we saw in 1.8, which is a really easy kind of concept, before looking at some more of these two-dimensional transformations that were kind of similar to 1.8, and we'll try to figure out how to get matrices for those as well. So let's start again with kind of an easy one here. So from 1.8, we talked about the contraction mapping, right? So the contraction mapping here, when we apply the transformation to a vector, you just multiply the vector by a constant. And in this case, our constant is going to be between 0 and 1, right? So when we multiply a vector by a constant between 0 and 1, it just makes it smaller. For example, let's pick a vector in R3, and let's define this linear transformation, right? So you apply the transformation to a vector in R3, just make the vector 1/5 the size, right? So you multiply each entry by 1/5. So kind of going back to our definition here, if we're trying to think about where this linear transformation exists, right? The things you plug into the transformation are in R3, and when you multiply it by a constant, it stays in R3. So just trying to use that notation up there. Our x's in this expression are three-dimensional, and what comes out is also three-dimensional because you're just scaling it. So this transformation receives vectors in R3 and sends them to R3. So we're remaining in the same dimension here. Okay, so since we're on R3, we want to think about the vectors, the E sub I vectors in R3, right? I kind of wanted to think about what dimension we're in here, because I need to know what vectors to pick, what jth column we're in Rn, right? So n is 3 in this case, and so we're going to pick vectors in R3, and in R3, there's 3 E sub i's. Right, so in R3, E sub 1 looks like this. Right, the identity matrix in R3 looks like this right here, right? So we just wrote these down a second ago. These are the ones we're going to be working with on this page. So E1 was that one. E2 is the middle column. And E3 is the right column. That's a 1, that's a 0. So what we're going to do is we're going to apply this transformation to each one of these columns, and that, by definition right here, will be the matrix we're looking for. Right? In other words, the matrix A that we want to find is going to be this transformation applied to these columns, just by definition up there. So let's do each one of these things. It's very straightforward. When you apply this transformation, you just multiply the vector by 1/5. That's exactly what that says. And so when we apply it to E1, you're just taking E1, multiplying it by 1/5. It just puts a 1/5 in that first spot. Right? If we did the same thing with E2, it's going to put a 1/5 in the second spot. And when we do it with E3, it puts a 1/5 in the third spot. And so those are the three columns of the matrix we're looking for. Okay, right, so using this information, these are the three columns we found. Those goes right into the matrix A. So the question is, what did we just figure out? Right. So what this theorem is saying is anytime we have a linear transformation, we can represent it using a matrix. And so, this is a pretty easy linear transformation. It just says take a vector and multiply it by 1/5. But the other thing that we just figured out is you could either multiply the vector by 1/5, or you could multiply it by this matrix A, and you'll actually get the same result. Okay, so let me just show you what I mean by that in an example. So what we just found, notice. So one thing we can do with this transformation is just use the definition, right? If we want to apply the transformation to a vector, you can just multiply that vector by 1/5. And if we're in R3 here, it would look like x1, x2, x3. And if we multiply that in there, we just end up multiplying each entry by 1/5. Okay, just by definition. So not using the matrix, this is using the definition of the transformation. Just multiply each entry by 1/5, right? Well, what we just found out is we could also just use this matrix instead. We just found out the other way to apply the transformation to a vector is by multiplying it by matrix A for this matrix right here. Right? And so let's multiply this matrix by the same vector, the same general vector, x1, x2, x3. Right? We know how to do that matrix multiplication. We would take this vector, kind of turn it sideways, do linear combinations of each one of the columns, and what we'd end up with is the exact same thing we just wrote down right there. Okay, so again, this is a very simple, straightforward example for the first one. And what we've just shown is applying the transformation of this contraction, we could either just go ahead and multiply the vector by 1/5 and get this, or we found this matrix representation, which allows us to take the vector and multiply it by that matrix and get the exact same outcome. All right, cool. So in the next couple pages, we're going to do the same thing, but just with examples in R2, right? So this was an R3 to R3 example. We're going to look at some examples on the next page, which are R2 to R2. Okay. And in each one of these transformations, we're being shown a box being transformed. And using that image, we should be able to apply the theorem we just learned about and determine the matrix A. Right? So find the standard matrix A for each of the following linear transformations. And in each case, the transformation is accepting vectors in R2 and it's keeping them in R2. In other words, it's taking a two-dimensional picture and just changing it around. And so what we're going to do is what we did in the last page. We're going to apply the given transformation. We're going to figure out what the transformation is looking at the picture. So in each case, to the two vectors in the 2x2 identity matrix. So to E1 and E2. Okay. So this first transformation is a reflection through the x1 axis. And what's going on here, what the arrows are showing, is it's showing an old box. So this was like the original box that might be right here. And it's being reflected around the x-axis to where the blue box is right now, right? And so what we want to think about is what happens to the vectors e1 and e2. Right, so the vectors e1 and e2 are actually on the original picture, right? So this is the x1 axis, the x2 axis. So that the vector 1, 0 is right here. Right? This is 1, 0 right here. And e2 is the other side of this box, 0, 1. And so if we think about what happened to those two vectors, we can just kind of look at the picture and see that, oh, this vector didn't actually change when the box flips over, and this one actually flips over here. And so actually these two answers are the answers we're looking for. Or we can do it, actually write down what the transformation is and apply it to those two vectors, and we'll get the exact same answer. Right, so what this transformation is doing in words, let me just write this down, it's reflecting through the x1 axis. And so it's flipping over the x1 axis. And so when you flip this way, the x1 values don't change, but the x2 values become negative. Right, so x1 values stay the same. x2 values you multiply by -1. In other words, if we want to apply this transformation to a vector in R2, right, in other words, you apply the vector to x1, x2, it's what we just figured out is you keep the first vector the same, the first entry the same, and you multiply the second one by -1. So here's a definition of that transformation. Very similar to what we just wrote on the last page, right? This is what we had as a definition on the last page. Multiply the vector by 1/5. This is telling us to keep the first entry the same, multiply the second entry by -1. And so let's apply this definition to these two vectors. Right. So using this definition, let's apply it to e1, and let's apply it to e2. Right. So let's apply this transformation to 1, 0, and 0, 1. Keep the first entry the same, multiply the second one by -1. So in this one, keep the first entry the same, multiply the second one by -1, stays 1, 0. This one, leave the first entry the same, multiply the second one by -1. And so these are the two columns of the matrix. Okay, what we just found out, let me maybe bring it up here, is that our transformation equals A times X for matrix A being those two columns, 1, 0, 0, -1. That's sort of the final answer. Right? In other words, let's apply it. Right? For example, let's see what happened to this dot right in the middle of there. Right? So that's the original box, the green one, and it gets flipped over, and so this dot would end up down here. All right, let's show that. Let's apply the transformation to that point in the middle, which is 0.5, 0.5, right in the middle. Right. Well, what this is telling us to do is to multiply this vector by the matrix we just found. And when we do this multiplication, these multiply and you get 0.5. And these multiply and you get -0.5. And so that's exactly what this point is right here, right? We applied the transformation to the top point. It flipped it down to this bottom point right there. Now, usually in person, got plenty of people to do some groups. I usually have people split up in groups and looking at 1 and 2 of these transformations. You know, people really get this stuff, end up looking at all of them. People who need some help, I oftentimes come around and try to help. And so I would strongly encourage you, if you feel good about this, to think about a few of them at least. I think that the two on the rest of this page aren't too terrible. The ones on the next page are a little bit more challenging. So take a second to think about it. If you still need me to maybe look at one or two more, that's fine. But at some point, please do pause this video and see if you can come up with one yourself. Okay, so I'm going to do the second one though. If you feel good, pause. If not, listen to me do this one too. Okay, so on this this transformation, we're reflecting through the line x2 equals x1. In other words, the original box is right there, but then you just sort of flip it around like this. Right? You flip it around that line. And so this is kind of telling, this sort of tells us what happens here. The x1 and the x2 values switch. Right? If you switch the x1 and x2 values, then the graph ends up flipping over like that. And so in other words, the definition of this transformation, if we apply this transformation to a regular vector x1, x2, we just switch the values. So it equals x2, x1. Right? This one went up top, this one went in the bottom. They flipped. And so let's just apply the transformation to the 2 points E1, E2. So let's apply the transformation to 1, 0. We're going to apply the transformation to 0, 1. Right, we're trying to see what happens to the two columns of the identity matrix. Well, we just flip the values is what this is telling us to do. So 1, 0 becomes 0, 1. 0, 1 becomes 1, 0. And so these are the two columns of the matrix. Again, what I'm just doing here is I'm applying to E1, E2, and then I'm using the fact that this is telling us that those are the columns of the matrix A. And so what we just learned here is that this transformation can be written as matrix multiplication. The matrix where those are the columns, 0, 1, 1, 0. So that almost looks like the identity matrix, except the 1 should be on the other diagonal, right? And again, just see how that works, right? If you apply the transformation in general to some general x1, x2, and you multiply by that matrix, right? You multiply this here, the x2 multiplies that 1, and it's going to end up on the top now. The x1 multiplies that 1, and it ends up on the bottom now. Oops, that should be a 1. See how that worked? It's kind of cool. Oh, I should have mentioned this too. The reason that we oftentimes want to represent a linear transformation as, say, matrix multiplication is because it's much faster. Now, these are just sort of toy examples. These ones here, these are kind of very basic, but we had talked about like Snapchat or some larger image processing type application. If you're trying to do something with a big image, multiplying by a matrix is oftentimes much quicker, especially on a computer, than carrying out instructions or some other way that a linear transformation might be implemented. Okay, let's look at the third one on this page. We're going to do the same thing. Let's understand what's going on in this one. So we're reflecting through the line x2 equals minus x1. So it's a similar kind of thing as the last one, where we kind of flipped around a line, except we're flipping around a different line. So again, this would be the original up here. And what we're doing is we're taking the original and flipping it around this line right here. Okay? And so this is basically telling us what's going to happen. x2 becomes negative x1. Well, that also means that if you multiply both those signs by negative 1, that means that x1 becomes minus x2. Right? And so this is sort of telling us the transformation. This is telling us that when we apply the transformation to a general vector, x1, x2, x1 becomes, this should be an x1, excuse me. x1 becomes minus x2, x2 becomes minus x1. So this is the transformation. And then we just apply that transformation to E1, E2, and that'll be the matrix. So we do this, using this definition, right? So minus x2 minus x1 becomes 0 minus 1. And this one becomes minus 1, 0. So these are the columns of matrix A. So we just found that we could apply this transformation by matrix multiplication where A has these columns. Now there are several more on the last page, but they just get a little bit trickier. Where we're generalizing instead of just flipping around a line where we have, the relationship a little more straightforward. We're generalizing a little bit more, and so we're going to take it maybe one step further on the next page. So the first two here, you can see is horizontal contraction or expanding versus vertical contraction or expanding. And so the horizontal one is like taking an image and either stretching it or shrinking it this way, right? So it's not getting taller at all. It's getting wider or shorter side to side. And the opposite's happening here, right? It's not getting wider. It's getting taller or shorter. And so the one on the left is the contraction. Obviously, it's getting smaller. And the one on the right is the expansion in both cases. Right. And so the contraction on the original one would be a little bit bigger than this. Right. The original one would be kind of like out to here, and then it's getting smaller. And the expansion one, the original used to be smaller, maybe in there, and then it gets bigger. Okay. And what you can see in both these cases, just to be clear here, this kind of green thing was the original that I was drawing. Again, in both cases, they don't get taller, but they get wider, right? Or shorter, right? Shorter if the k is less than 1, bigger if the k is bigger than 1. And so if we're kind of thinking about in words, if the height doesn't change, the height is the x2 value. And so what we can say is x2 values stays the same. It doesn't get taller. But the x1 value is a thing that scales, right? If k is bigger than 1, it gets bigger. If k is less than 1, it scales down. And so x1 gets scaled by a factor of k. In other words, that's sort of the word version of this transformation. If we apply this transformation to a general vector, the x2 value stays the same as what we just said. x1 gets scaled by k. Okay, so then once we have once we have the definition, we have something to work with. We just apply it to the columns again. So let's apply this transformation to 1, 0. And we're going to apply the transformation to 0, 1. Just in case you happen to take a break or you're forgetting why we're doing that, we're following the definition on the first page. We're trying to apply the transformation to the columns of the identity matrix because that will tell us the matrix representation of a linear transformation. Right, so this is E1, this is E2. All right, so this says multiply the first entry by k, keep the second entry the same. So this becomes k 0. The second one just stays the same, 0, 1. So those are the columns of the matrix. So T of x equals AX, where A equals those columns. Now you can imagine the second one is very, very similar, right? Now, instead of x2 staying the same, x1 getting scaled, right? They're not getting wider, and so x1 is staying the same. And the x2 is the one that's getting bigger and smaller. And so we have a very similar transformation, but instead of scaling the x1, we're scaling the x2. And so we get a very similar matrix instead of the k is going to end up down there. Right, if you see what I mean, you know what I mean. Let's do it though, right? So we're scaling x2 now. And so if we apply the transformation to 1, 0, it stays 1, 0. And if we apply the transformation to 0, 1, the k ends up multiplying down into the bottom. And so those are the two columns. Oops, off the page, excuse me. So our matrix has those two columns. Right, so if we want to, in other words, notice what happened here. If we want to scale in the horizontal direction, the k is in the upper left-hand corner. If we want to scale in the vertical direction, it's down here, right? Because this one ends up multiplying the x2. This one's going to end up multiplying the x1. Take a slightly different approach on the last one. In all the previous ones, we've sort of come up with a definition for t of x. Let's just look at the picture in this last one, since it's a little bit more confusing. It's going to be harder to come up with an actual maybe formula like we did. Let's just look at what's going on here. So this is called the vertical shear. In 1.8, we looked at the horizontal shear. So in the vertical shear, it's kind of like you grab the original on the left and you grab the right, and then you either move the right up or down, but you keep the left the same, right? And so if we're thinking about E1, E2, the original might be over here. And let's think about what happens to E1, E2. Well, E1 is 1, 0. So that's this vector right here. And E2 is 0, 1. So that's this vector right here. What happened to those two vectors? Right? So if we grab this on the left and grab it on the right, and we move the right up or down, the one on the left stays the same. Right? So this point doesn't actually move in either case. It stays there or it stays there. Right, so E2 is actually not moving. What's moving is E1. E1, if you grab the right, you either move it up or down. E1 is either going down by a factor of k, or it's going up by a factor of k. Right? And so let's do it in words first here. What I'm seeing word-wise is it seems like the x2 value on the left-hand side here, this 1, is not actually moving. But the x2 value on the right gets scaled by a factor of k. Increases or decreases by k. And x1 in all these cases is always staying the same. In other words, when we apply the transformation to 0, 1, 0, 1 stays the same. And when we apply the transformation to 1, 0, it becomes 1, k. Right? And so those are going to end up being our columns. Right? We can very clearly see, looking at the picture, that when the transformation is applied to 1, 0, this one right here, this one right here, it becomes 1k. And when we apply the transformation to 0, 1, it stays the same. And so that means our transformation can be written by matrix multiplication with A, where A equals those columns. Now, most of what we've done in this section, all of what we've done is in R2 for them. Well, we did one in R3, but that's mostly because we can visualize R2, but this has large reaching applications, and we'll see some other dimension changes in some of the homework. In the second half of the course, we're going to be looking at one-to-one and on2, and that's going to be a separate video.